Hi everyone, myself Vivek Raut. So I'm making this video to explain the bias variance trade-off. So how I'll be explaining actually, so I have divided this video in three parts. In the first part, I'll be explaining the real-time machine learning example with the machine learning equation, the basic equation. Then the going forward, I will explain the bias and variance trade-off, like the definition of bias and variance. And the last part, I'll be showing you the equation from the machine learning point of view, how the bias and variance coming into the picture, and how we are using it actually. So I will decompose the equation. So let's go and start.
So let's start with the real-time problem. So if you see carefully here, I have written down one equation. So what we are trying to show it here actually, we are trying to predict a house price given house of size of house, sorry. So what happens when a machine learning problem, we are trying to predict some certain variable, if the dependent variable and the independent variable will uh, have some certain kind of relationship, which is not known, which is not known. Now what happens? What we do actually, we are trying to predict this relationship using our dependent. We are trying to find out the pattern between x and y. So, but in real-time problem, if you see, other than the relationship, there is a noise also the model has. Not model, the equation, the real-time problem has real-time because house of price can be dependent on some other circumstances which is not dependent on x, which cannot be predicted actually. So this is what called the random noise. So I will take an example to explain the random noise actually. So suppose you are trying to predict, classify certain patients, the certain number of patients, is if the patients are allergic to some kind of drugs or not. So as a input variables, the dependent independent variables, you have the blood compositions, the blood readings of those patients. But what happens, suppose in certain day you are trying to predict one patient if he or she is allergic to some certain kind of drugs, but this can be dependent on the readings which we have taken earlier, and those equipments can be faulty, and can occur some kind of noise in the whatever the data we have. So this kind of noises which we don't have in our control, but it is affecting my predictive variable, uh, predictor. So that kind of those things are called random noise. But if you see, these random noises are having some certain kind of properties. So I'll write down here. The properties in means these noises are having mean as 0. The expectation value of noises are 0, and at the same time, and the variance also we are able to understand. So this is the variance also given. Suppose you have the variance and the mean is 0. These two properties you um, try to remember. Going forward, we'll use this property. This is written like this: epsilon of like e of epsilon squared actually. So now let's go and try to understand the later parts. So what happens in real-time scenario, we have the unknown relationship between the x and y. So what we try to do actually, we try to find out a f hat of x which is closest to f of x, that means this is closest to actual y. This is our target actually. This is what we try to find out. How we can find out these things actually? So we have certain x data. So in the training data, using training data, we try to find out the relationship. In in while trying to find out the relationship, what we try to do actually, we find a loss function that I think everyone knows. Suppose as this is a relationship regression problem, in uh, here the loss will be MSE, mean squared error, and here our scenario, in our case, the mean square error equals to e of the expectation value of the mean squared error. E is, you can think about the average value, e of y minus f hat x whole square. I think it's clear, right? Because if you see, we have the x value. We are trying to find out this f at x, and each time we are finding a difference and squaring it because to balance the those signs actually it can be positive or negative to get the average value. So this is how the MSC. I think you guys are aware of the MSC, right? This should be the prerequisite actually to understand the bias variance trade-off. So we'll go further. So this is all about the MAC and the expression about this y equals to fxa. So now we'll go and move forward and we'll talk about the bias and variance. So next time I will be explaining the bias and variance quickly before going to the bias variance trade-off. So what is bias? As I spoke about the house price and the size of the house problem statements, so here we are trying to predict the house price. So while trying modeling the data, um, if you don't have the enough training data, suppose, or the model is weak, in that case, so this is the scenario. If you see, this is suppose x-axis the size of the house, and y-axis my price of the house. That this red line is showing my model, suppose linear regression. But if you quickly it is not um, able to understand the pattern of the data, and this modeling is very weak. In this case the bias is high. So when we say the bias is high, in that case the training error is pretty high. And what is high variance? High variance is when you are trying to model the data, the model is following the data so blindly, and suppose see, so it is following the data very like frequently, it is going to the data each data points. And what happens, suppose you are trying to test the model with some unseen data, it will throw more error. In that case the testing error is very high. So with the bias is high, the training error is pretty high, and with the variance is high, the testing error is pretty high. So what is our real-time scenario? What we are trying to get is low bias and low variance, and this is how it will look like. Now let's go and try to understand the equations of bias and variance in for each. So th- this is I'll talk about what is bias. So bias is a average value or prediction to the true relationship of fx. So prediction is f hat x, and that expectation average of that. So why I'm saying the average value or prediction actually, so f hat x actually are random variable in this case actually. So this our f hat x, so this is a random variable, and it is affected by the randomness of the training data. When we say this, that means what happens, suppose you have a population, and you are trying taking out a sample of that population, you are creating a model, you are predicting, and that prediction the model is f hat x. Then again you are repeating the same experiment, and you will have the number of predictions. So in that case f hat x we can say as a random variable, because you are trying to repeat this experiment multiple times. So when we say the bias, what is the meaning of bias? Is actually, suppose you have a straight line, and if x is the actual value, the relationship which we don't know, but if hat x, so for some certain value, it's one experiment we have repeated, so using some sample of data from the population, and this is the value we are getting. So this difference, whatever you're able to say, this is the bias actually. This is what the bias is depicting. So what we are trying to say, f at x, if it is getting closer to the fx, the difference will be low, and this is what we are trying to do over here actually. Now we'll go to the this variance actually. So what is variance? Variance is mean square deviation of f hat x from its expected value, expected value e of f hat x. So what we say, as I just told, um, if hat x is a random variable, so what happens if we draw plot a curve? It can be normal distribution, mostly it will be normal distribution in real-time scenario, I told, right? um, Real-time scenario, suppose this is my expected value, and f hat x have some one value, because if you think closely, the mean of f hat x is a um, constant value, because average value will be constant, but f hat hex will vary. So this is kind of finding a variance of normal random variable, how we used to do for the normal distribution, some other distributions. This is what we are trying to do. If the curve is spread out, if the difference is high, this variance is high, in that case we are saying uh, suppose if we are trying to give some unknown data to the model, it will throw more error in terms of the testing error. Actually, this is what the bias and variance is all about. Okay, now let's start with the bias and variance decomposition. So if you see carefully, so this is my MSC term, and e. So what we can see, the y, we know y equals to fx plus epsilon. This is my the equation, like the first part only I have written. And now what we want to do, actually we want to expand this term actually. So this is my a, uh, this is my a, and epsilon is my b. What, and this is my a minus b whole square. If you see carefully, so if we declare fx minus f hat x equal as a and epsilon as a b, this term will come a minus b whole square. So this is my, sorry, a plus b whole square, and this is my 2ab term. Okay, now what we have to do, actually see carefully this term. Now my this term, sorry, my this term fx minus f hat x. So fx equals to is constant, fx is constant, right? Because for particular x, I'll get the exact one value, that's why it is a constant. But f hat x is my random variable. I told earlier, this is my random variable. So this whole term, this my whole term fx minus f hat x equals to random variable, and epsilon is also a random variable. Epsilon is also a random variable. Epsilon is also a random variable. This is my noise, random noise. So in expectation properties, if two random variables rv1 multiplied by rv2, if I have this way, I can write e of rv1 multiplied e of rv2. This is what I have done here, over here. Actually, if you see, this is what I have done now. And in the second term also, it is linearly distributed actually. So this whole term is linearly distributed for e expectation, right? This is how, like I have distributed the e term. That's the property of the expectation. So and if I and that, and coming to this random variable, whatever I have showed here, and this term, the expectation of e, this term is 0. I have already told, like, because my random noise is means zero centered, that's what I have told. And this term, my expectation of this is variance of, just variance of noise, variance of my random noise, correct? I believe it's clear. And so this whole term will become 0 because my e of epsilon is 0. So now I'll have only these two terms, and this term is called reducible error, reducible, and this term is called, sorry, irreducible. Now I'll take a minute and I'll try to explain why this is called irreducible and why this is called reducible. Though you should be able to understand if you understood the first part. So I'll explain the irreducible part. as I already told, my noise, random noise, is not dependent on x, but it is affecting the relationship between y and x, because it is affecting the y, but it cannot be predicted, or cannot be we cannot get the relationship between random noise and x, right? It's not dependent on x. And in our when we try to model any machine learning model or deep learning model, we have x and y. Suppose it's if it is supervised, I would say. And so when we have the x, and we don't know about the noise, right? Because we cannot model the noise. So that's why the irreducible error is called this variance term. But talking about the reducible error, f hat x, what is f hat x? So this is the term which we can manipulate based on my training data. So if we can get the f hat x, which is closer to the real relationship f x, so my this whole error will decrease. That's why we can say this is a reducible error. I believe it's clear, right? Because this whole term we can bring down by manipulating the training data with trying with multiple training data, multiple set of training data actually. Now we'll go to the next part. And now, okay, so uh, this is my term equation, and what we have done actually. So I have added this two term e of f hat x, just subtracted and added over here actually, just to get the equation in my required format. And as I told, expectation by properties, we can like linearly distribute any equation. That's what I have done. So so if I see carefully, this is my a term, this is my b term, this is my a term, this is my b term. So I can write a minus b whole square. That's what I have done here. So a square plus b square minus 2ab. And but carefully, if you see what I have done, actually I have just manipulated the terms before after, because a minus b whole square and b minus a whole square is same only, right? But the other terms are same. That is all about. Now if you see carefully what I have done here, so this term is bias, my this term is bias, and this term is variance. That's what I have like written, like it's written here, right? Because if you don't remember, I have already explained these two terms. So if you go and see here, so here I have to explain those two terms. Like you can go back and watch the video again if you have any doubt. So this is my equation, right? Bias square and the plus variance. But what about this equation? How come this now I'll talk about this equation. 2 of uh, 2 multiplied expectation of a and b. This is my a term, this is b term. Now when I'm saying this is my a, this is my b, but if you see carefully, I have not written the e term. So this works as a constant. Why? Because see, I'll explain. Mm, yeah, if x I have written is constant, if hat x is just a random variable. Now e of if hat x, this is my constant term, right? Right, this is my constant term. Now see carefully, if x is constant minus e of f hat x, this is also constant. So this whole term will be constant. If x minus e of f hat x, this whole term is constant, right? That's why, and applying expectation of any constant term equals to is constant, right? That's what we know. That's what we have done actually. We brought out this term outside as a constant. Now I need to apply the expectation for f hat x minus e of f hat x. Only this term is left as a variable, I would say. Now, sorry, here the x term will come. Now, what we can do actually, we can linearly distribute. This will be f hat x, and this will be e of f hat x. Now If you think carefully, this whole term is a constant, right? This is constant. I already told. Now applying constant to any constant, applying expectation to any constant equals to a constant. So this whole term I can, this whole equation I can write e of f hat x minus e of f hat x, right? Just go back and watch. I know it's little bit like you can get confused, but just go back and watch the video. It will be like you'll be able to understand. So now this whole term I can write like this, and this is 0, like, right? This is 0. So this whole term will become 0, right? Now what I have actually as equation, I am left with bias and variance term. Now write carefully what I have as a MAC equation. So what I was trying to derive, as a MAC E of y minus f hat x whole square equals to, now what I have actually, I have bias of f hat x, this term square, plus variance of f hat x plus this irreducible error term. This is what I was trying to get actually. Now what is the use of, sorry, now what is the use of this term? So this term, like I can manipulate these two variables to bring down my MAC. This is my MAC, so that I can get the actual effects. This is the whole use of bias and variance decomposition. Like I have explained the bias and variance decomposition, and if we manipulate, if you can bring down the bias and variance, it will affect the MAC. So this is all about the video.